Hello, everybody out there in YouTube land. This is Good Times for All, or Zachary Zabala here if you prefer. This is going to be a sequel video to the one I made about the curvature calcular addition due to angular resolution and limitations of physics. This will be looking into perspective along with angular resolution and how it all kind of works together. I drew a few pictures here to hopefully help. I know when I do my research, I always love having some pictures to look at. It just makes it a lot easier to understand what they're trying to say. So first off, we're going to look at this picture right here. Now in this picture, the bottom red line here, the straight line, would be your ground level or the water level if you'll have it. Up here at the top, we're going to say is the path that the sun is taking, or maybe a plane flying overhead would be taking. Now, any object that is moving in a straight line overhead will start off at your horizon line, which is eye level here. It'll come up from the horizon and it'll hit a certain point which is directly above you, and that will be called the zenith. And then once it hits that point, it will start lowering down into the sky until again it hits the horizon line and disappears. Now over here we have in the orange is the angle of resolution limit. There's your guy standing there. Again, the horizon line is in the middle, the little black line in the middle. So for a certain distance above and a certain distance below, at that angle, you cannot make out any objects that are within that angle, any light sources. It'll just all be blurred together. It'll look like a straight band along the horizon. Just imagine anywhere you go to here, and then say there's your horizon line, you would cut that off, and at that angle, or however many feet that was taking up, you'll cut that up, and it goes all the way along the horizon. It just isn't where the buildings are, or boats, or whatever you're looking at. It goes all the way along the horizon. You have to remember that. It's not just it's gonna cut off the air, it's gonna cut off everything. The water, nothing will be seen within that. It'll all be blurred together. So here in this first picture we have at the top, you have your little guy standing here, and we're going to imagine that all these matchsticks are the same building. The only reason they're getting smaller is because they're getting further away, and they're getting smaller due to perspective. Now, yes, I know things can be magnified due to atmospheric distortions and whatnot, but in this occasion, we're going to say that everything's nice and clear and beautiful, and it's just getting smaller due to perspective. Now down here, we have our candy cane, which the ground will still be at this level, but what our little guy over here sees is it coming up to the horizon line here. Ground rising due to perspective. Our black line in the middle there is our horizon line, and the orange above and below is our angle of resolution limit. So nothing in between there can be made out. So as you can see, our building, when we're standing nice and close to it, we can see the whole thing, and the angle of resolution is nothing. We're going to pretend, now none of this is to scale, folks. This angle is much smaller, much smaller. And then when you go, further away, you can still see the whole building, but the building is smaller due to perspective. Now you get over here, we'll just say it's over here. So you have the building, let me move this one too. So you have the building here, and it's rising along the ground. Well, it's not rising, but it's going along the ground, which rises to our eye level. and our angle of resolution catches it right there. So the whole bottom of that building right there, you're not going to be able to see. So what would you say, about a quarter of the bottom of that building is cut off because of perspective making it smaller and your angle of resolution cutting off the bottom, which is also rising up to your horizon line. And then you look down here, and perspective has made the building so small, and the angle of resolution has gotten so big to now that, we'll say, we'll move that up a little bit. About half the building is cut off now, instead of a quarter or whatever. None of it's to scale. It's just to show you how it works. So all of this stuff has to be taken into account when we're looking at this stuff. And that's why buildings and everything like that, the bottom starts disappearing as it gets further away. Oh, that was a good one. Okay, now here is the sunrise and sunset. Our sun is going to be this dime. Here's our little guy standing here. Here is the ground rising up to the horizon line. Same here. None of it's to scale. Maybe this line right here, where it crosses, is supposed to be right here, where this comes together. None of this is to scale. It's just showing you how it all kind of coincides and works together. And then here, we're going to say the sun is just moving over our heads at the same elevation. I'm not saying that's how it actually works, but for this demonstration, we're going to say that if it did, this is what it would look like to us. Now this is your due north or south. If you're in the northern hemisphere, you'd be looking south. Southern hemisphere, you'd be looking north, and that would be your zenith point. That'll be, 270 degrees, or I'm sorry, 180 degrees south, or 0 degrees north on the compass. So the sun is over here at the horizon line, okay? Now, we can't see it yet because it is beyond our angle of resolution limit. Our angle of resolution limit is bigger than the sun right now. And as it comes into our view above the angle of resolution limit along this line right here, which is still just a flat line, but this is how we see it, you'll see the top rising first, just like we see in reality. And as it crosses over our angle of resolution limit, you can see it rise just like it does. And it'll go up in the sky during the day, and it hits that midpoint, that midway, which is solar noon, the highest point of the day, and it'll start descending back down towards your horizon line. And as it gets here to your angle of resolution limit, you can see that the bottom will start disappearing first, just like we see in reality. And it would be gone right there, beyond your angle of resolution limit. And really, all that it's doing, all that it would have to be doing is this, moving above our heads. And we would see it do this, rise, hit a certain spot, and start going down and set. It's that simple, folks. So I hope that helps. I don't want to make this too long, so that's going to be it. If you have any questions or anything like that, shoot me a comment. I hope this helped clear some of that up. And yeah, this right here has to be added into our curvature calculator, the angle of resolution limit. So when you have this over here, and the building is so small because of perspective, you also have to take into account that the further away it gets, the bigger, not the bigger the angle of resolution limit is going to get, because it's an angle, but the more space, the more amount of feet or meters that angle is going to take up. All right? So we have to take all this stuff into account when we're trying to determine what we are seeing and how we are seeing it. I believe most of it is due to our eyes and how they work. So that's going to be it. This is Good Times for All signing out. And as always, thanks for watching.